So in this lesson, there are three proofs, and I've added a fourth proof between B and C to make problem C a little bit easier. So in the first proof, we're trying to prove that angles A and C are congruent. And I understand that we have accepted that idea since chapter 1. We talked about the fact that isosceles triangles have one line of symmetry, which in this case would be through point B. And when you fold that triangle in half, angles A and C would match up. But that is our way of investigating it and to come up with a justification for why it works. But we're trying to develop some formal proof here, and so we're actually going to go through and show that it really does work every time. So in doing our proofs, many of the problems we're doing involve triangles. And I'm not talking about a single triangle in the case of ABC, but usually two triangles, so that I can use my side, 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 angle, and so on patterns, congruence patterns, to help me justify that these two triangles really are congruent. So in this particular problem, there's only one triangle, but we can actually divide the triangle up into two triangles. The issue is there are lots of segments that I can draw from point B to line segment AC. So what we want to do is, well, we want to make sure we draw in a segment B, D, so that segment is actually helpful or useful to this proof. So think about it for a moment. What kind of segment could we draw in or construct from point B that actually would add additional information to this picture and would allow us to prove the triangles are congruent. When we have an idea or a couple ideas, turn the video back on. So there really are two good segments that could be chosen here. We could make line segment BD an angle bisector of B, and that would allow me to say that these two angles here would have to be congruent to each other if BD is an angle bisector. Another choice that we could make would make BD a perpendicular segment to AC, and that would allow us to create right angles at D, and that would give us another piece of information. So for this problem here, we're going to let BD be a perpendicular segment. So what we're going to do is line segment BD is perpendicular. This upside down T symbol is the perpendicular symbol. It's perpendicular to line segment AC. And basically our justification for this is that we just simply did a perpendicular construction. So we can construct things or add things to pictures if that in some way helps us. Consider for a moment, based on the current picture and with the two angles at point D being right angles because we get sort of perpendicular segments, do we have enough information now to be able to complete a proof? So most of our proofs for showing a triangle, two triangles are really congruent, usually involves three pieces of information. The only exception might be hypotenuse leg, but side, 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 side angle, side, and so on. We need three pieces of information. So I'd like you to continue this proof and draw down the additional four loops and see if you can identify the information necessary to show the triangles really are congruent. Keep in mind we're proving the angles A and C are congruent, so we can't use A and C in this proof because that's what we're trying to prove. So we can use the other information to actually finish this proof. When you're done, turn the video back on. So hopefully you said that AB and BC are equal to each other because it's actually given to us. And hopefully another choice here is that maybe let BD be equal to itself. Now that's called the reflexive property. So if you watch some of the earlier videos or if you were in class when I talked about this property, it's an algebra property which basically says that anything is equal to itself. And if you don't remember some of the properties, you can actually write a statement out outside the loop kind of justifying your thinking. So, for example, you can simply say a segment is equal to itself, and that would be basically what the reflexive property is saying, is that something is equal to itself. And then the third piece of information is actually coming from the fact that the BD and AC are perpendicular. So hopefully here you wrote that angle BDA and angle CDB, those two angles have to be the same measurement they're marked in blue as the same measurement. But the reason why they are the same measurement is because of the definition of perpendicular lines. We're talking about, in this case, segments, but we can use the word segments or lines. And basically, we have two things that intersect each other, forming right angles or equal angles. So this is enough information to be able to say that the two triangles are going to be congruent to each other by hypotenuse leg. So triangle ABD is congruent to triangle CBD by hypotenuse leg. Now we're still not done with the proof. What we're trying to do is prove that that the angle at A and angle at C are actually congruent to each other, and that actually is something we can actually prove now, because the two triangles are congruent to each other. So therefore, their corresponding parts are also congruent. So angle A and angle C would be the two pieces of the triangle that would match up. As the justification for this is simply 5 letters, CP, CTC. It means that corresponding parts, that's the A and the C angles, are of congruent triangles, that's the statement above, are congruent. So congruent triangles corresponding parts of congruent triangles are congruent. That's the CP, CTC as an abbreviation. So that's the first proof. So go ahead and we'll move on to the second one. So in problem B, we're trying to prove that the two angles I have question marks on are actually congruent to each other. And for this problem here, we actually should be able to get enough information because it tells us in the problem that we're starting with a rhombus. So I'd like you to think about how you compare up the information so that you can make a proof here showing that these two triangles really are congruent using the fact that we have a rhombus. When doing proof, I would recommend, especially when you're working with quadrilaterals, are we looking at a situation where it's better to think of this proof as one triangle is a reflection of the other, or that one triangle is a rotation of the other? Because in doing reflection, the sides you're going to pair up in your congruency statement, especially for a rhombus, are going to be different than if you approach this problem as a rotation. So like you think about the problem, here we have a proof here, 4 steps, and then we're going to add in that 5th step, which actually is going to show that the two angles really are congruent to each other. So see if you can complete the entire proof, and when you're ready to see the proof being done, turn the video back on. So this proof would be done much better as a reflection. So because it's a rhombus, all 4 sides are equal. Because I want to prove the triangles are congruent, I want A, B, and to fall on top of BC. Because again, if I look as a reflection, then I'm going to put the angle here, the first question mark, on top of the other angle with the other question mark. And so those two segments are equal to each other because the definition of a rhombus states that all 4 sides are equal. And that would then I can let AD be equal to DC for the same reason, definition of a rhombus. The third piece of information hopefully you chose was the shared segment. So DB is equal to itself. That's the reflexive property. So both triangles are congruent. So the ABD is congruent to triangle CBD. So I'm using reflection here, so the last 2 letters are actually in the same order. If it was rotation, then the B and D would be switched on one of them. So they are congruent to each other by side-side-side congruency. And because the triangles are congruent, that means all their parts are congruent. That would be the 3 sets of angles. You know, the only one we care about here is the ABD and the CBD. So these 2 angles, because we did the proof as a reflection, those two angles are the corresponding parts, and they're congruent to each other because the triangles are congruent. So the justification is CP, CTC. So in this third problem, this is actually not in the book. And I felt that doing this proof first would make problem C a much easier proof to do. So we're going to try to prove here is that line segment A, B, and CD, those segments are equal to each other. And we're going to do the same thing with AD and BC. So basically the idea here is let's prove that the opposite sides of a rectangle are equal in measure. The suggestion they made in problem C, it actually was an excellent suggestion, which let's state right up front that ABCD is rectangle ABCD is a parallelogram. And that is something that we already know because we've actually proved that. So that anytime we prove something, it's called a theorem. It's like theory. So in geometry, we call it a theorem. So we're just going to simply call it a theorem at this point. That on Tuesday, this actually is one of the problems from a previous lesson that we proved that a rectangle was actually a parallelogram, and the lesson before that, we actually proved the rhombus was a parallelogram. Because we have a parallelogram, that means we have to have parallel sides. Go ahead and mark those. So AB and CD are going to be the parallel sides, and BC and AD also are the other pair of parallel sides. Because we have parallel sides, then that means there are two more things that we can say about the shape here, because the shape is now defined as a parallelogram. So think about how using the parallel sides might give me two more pieces of information. Can you come up with a third piece of information to be able to say that the triangles are really congruent? When we're finished, we're trying to prove that these pairs of sides are actually equal to each other. So if we can prove this, then these two things here should hopefully follow as corresponding parts. When you're finished with the proof, turn it back on, and we'll continue with the conversation. So because we have parallel lines, I'm hoping you start thinking about congruent angles. Because anytime we have parallel lines, we have correspondings, alternate interiors, we have same side interiors and exteriors. And as I mentioned in class multiple times, normally when we have quadrilaterals cut into triangles, alternate interior angles are the pair of angles that we will be able to identify if we have parallel lines. So angle B, AC is congruent to angle DCA because alternate interior angles are congruent when lines are parallel. And then the other pair of angles, angle DAC is congruent to angle BCA for the same reason. All interior angles are congruent. We need a third piece of information, so I'm hoping you chose AC is equal to itself by reflexive property. And now we have enough information to be able to say that both triangles are congruent to each other by angle side angle. So I'm going to leave that part here for you to finish off since I have 15 minutes in terms of my time. So angle side angle was the reason, and these were the corresponding parts, so therefore corresponding parts are going to be equal or congruent to each other because the triangles are congruent. So CP, CT, C. So on this last problem, problem C, which I'm going to leave for you to finish, we're trying to prove that the diagonal AC and DB are the same length. And my suggestion is think about the last proof. We actually proved that opposite sides of a rectangle are equal. And so can we organize the problem in a way to be able to prove that these two triangles actually have equal diagonals AC and BD? So think about what we did previously. Think about some of the other definitions and rules that we have, and can you come up with the proof to show that AD equals BD, AC equals BD? It's a real similar proof to the previous one. We have our three pieces we're looking for, which will give us the congruency, and we're trying to prove that the AC and BD equals each other. If you're using a previous proof, it's called the justification. Again, is the word theorem. So good luck on this one, and bring the problem back on Monday or Tuesday.